Okay, so what I want to do now is look at applications of extrema. So there are tons of situations where understanding the maximum minimum value of a function would be very important. We're going to look at a specific type of problem, one in which we're trying to maximize some sort of quantity subject to some kind of constraint. So I'm going to do this first with a kind of a quite pure mathsy looking example to illustrate kind of the fundamental idea, at least in the solution technique. So here's what I would call a motivating example. At least it's going to motivate the technique of solution. So the motivating example, let's do the following. So what is the minimum value the sum of two positive numbers can be if their product is 100. Great question. Okay, so it's kind of a pure maths question in a sense, but we'll see that this type of problem turns up all the time in actual practical applications. So the first thing I want to do is to, quantify the unknowns in this picture. What are we trying to do? We've got two unknown numbers. So let me do this first. So I'm going to quantify the unknowns. So the unknowns are two numbers, x and y. They're both positive, worth stating. So let's identify the objective. So that's really important. When you see a word problem like this, you've got to ask yourself, what are you actually trying to do, right? What is the objective of the problem? Identify the objective. So we want to minimize the sum. So we want to minimize the quantity x plus y. Okay, so that's the entire aim of the game. Now this would be silly, really. If that was all there was to it, the minimum quantity would be 0, wouldn't it? Because we've just set x to be 0, y to be 0, and that would be the end of it. But there's a constraint in the question, so we should identify that as well. So what is it? The constraint is the product is equal to 100. So that means x times y is equal to 100. Okay, so I've got two pieces of data then, essentially. I've got an objective, right, which is a formula, which is x plus y, and I'm trying to minimize that subject to the constraint that x times y is equal to 100. So this guy is called the objective. I'll call it the objective formula, maybe. And this guy is called the constraint equation. Okay, so we're trying to minimize a quantity, the objective, and notice it's a two-variable function. Now we've got a lot of experience in finding maxima and minima of single variable functions like f of x, but two variables, that's a different deal. We've got no techniques for dealing with this. So as it stands, there's no obvious way to proceed, but we can try to use the constraint to convert the objective into a single variable function. So let's do the following. Let's solve the constraint in one unknown and substitute into the objective. Okay, so what's the constraint? The constraint is x, y is equal to 100. That implies, well, let's solve it in y. Y is equal to 100 divided by x. Okay, so what does this tell us? Well, now, if I take the objective, I can replace y with 100 over x. So this is equal to x plus 100 over x. And it's a single variable function. I'm going to call it f of x. Okay, so at this point, what am I trying to do? I'm trying to minimize the value of this function subject to a certain condition. I'm trying to minimize this without really, I've basically put the constraint into the objective now. So this is kind of the constraint and the objective simultaneously in one form. If I'm going to find the absolute minimum of this function, I need to know the domain it's on. So I would say identify the domain at this point. Identify the domain and find absolute extrema. So in this case, it's an absolute min, isn't it? Okay, so let's think about the domain for a second. So the domain is interesting. I mean, if we just look at f, obviously you need x to be non-zero. So purely looking at f on its own, finding the domain of that function is everything non-zero. But notice the question imposes further conditions. Notice above, the quantities are positive numbers. So we know that x is non-zero, but certainly greater than or equal to 0. So are there any other conditions? Well, these two are coming from it. Notice also this up here. Well, that's the constraint. Notice x can be as big as we want. There's no restriction on how big x can be because we can always counterbalance it with a smaller and smaller y. So x is non-zero, it's positive, and it can be as large as it wants. That means the domain is equal to 0 onwards. The reason this is important is because when we find absolute maxes and absolute mins, it's important what the interval is. Is it a closed interval? Is it an open interval? All sorts of questions like that. Okay, so now what have I got to do? Well, if I've got this interval, I'm going to have to do, so it's an open interval, it's not closed and finite. It means I'm going to have to use my critical point theorem, or generally global sign analysis on the derivative. So let's work out the derivative. F prime of x is equal to what? 1 minus 100 over x squared. So let's go through the possibilities. So f prime of x is equal to 0. That implies rearranging this, x squared is equal to 100. That implies x is equal to plus minus 100. Remember though, the minus won't matter because we're only dealing with things which are strictly positive. Second, f prime, well there's a problem with 0 in general, but I'm only dealing with the function on 0 to infinity, so f prime is continuous everywhere. If I'm restricting 0 to infinity. So there are no type B points. So at this point, let's draw my number line. 0. I'm doing analysis on the derivative. I've got a point 10 in here, that matters. So then what am I going to do? Well, let's do f prime of 11. If I feed 11 in, it's what? It would be 1 over, so 100 over 11 squared, that's big. Okay, so this is going to be positive. If I do f prime of, I don't know, 1, let's say, this is certainly negative, it would be minus 99, so negative. This is a critical number. So what have I got? I've got it decreasing down to here, and then increasing forever. It's a critical number, so it's a relative minimum, but we know by the critical point theorem, this is an absolute minimum. So this tells you f of 10, which is equal to what? It's equal to 10 plus 100 over 10, which is 20, is an absolute minimum on the interval 0 to 100. Okay, so now what I want to do is I want to gather it all together. Maybe it's worth pointing out, I mean, if x is equal to 10, what's y equal to? Well, y, remember, is 100 divided by x. So these two things tell you that y is equal to 100 divided by 10, which is equal to 10. So this minimum is going to occur when they're both 10. So let's put that together. So let's gather it all together. Into one conclusion. So this is what I'd say. If x and y greater than or equal to 0, positive numbers, and xy is equal to 100, the minimum value of the sum x plus y is 20 when x is equal to y is equal to 10. So that's put all together. Okay, so that procedure is really the backbone of what we're going to look at throughout this chapter. So it's worth saying at this point, these kind of problems have a name. A problem like this is called, unsurprisingly, a constrained optimization problem. Constrained optimization problem. Optimization because we're trying to get an absolute max or absolute min of something, so an optimal value generally, and constrained because there's some sort of constraint in the picture. So let me now put together kind of a checklist of things you should do when you're trying to solve a problem of this nature. So let's do a basic strategy. Strategy to solve constrained optimization problems. So these are difficult. I mean, generally they're presented to you as like word problems. So the hardest part, in my opinion, is extracting the right information from them, mathematically speaking. I think when you're confronted with a word problem, everyone pretty much kind of panics at the amount of material thrown at them. Perhaps it's talking about a subject you don't know very much about. What you need to do is to extract the information carefully and methodically in the following way. So first of all, if you're given some sort of constrained optimization problem, you want to read it very carefully. And I cannot stress that enough. Take a deep breath and read it very carefully. The first thing you should look for in a problem is to identify what it is you're trying to maximize or minimize. So identify the objective quantity to be maximized stroke minimized. In the previous example, the objective was the sum of two numbers. Okay, that's the most important thing. So I really have to stress this. This is the most important thing, right? If you cannot identify what it is you are trying to maximize or minimize, it is absolutely impossible to do these problems. Right? So with all of these word problems, you have to think methodically. So the first thing is, what am I trying to maximize or minimize? What is the quantity? Generally, that'll be fairly obvious. But write it down. The next, often you'll be given problems which involve geometric objects, cylinders, rectangles, walking paths, things like that. So perhaps draw a picture. Perhaps draw a picture and label the unknowns. In this class, generally speaking, there will be two unknowns. That's not true in general at all. You could have many degrees of freedom in a problem, but generally speaking, any constrained optimization problem in 16a will involve 2 degrees of freedom. Okay, an x and a y, a radius and a height, all sorts of things like that. Okay, next. Once you've done that, you want to combine these two things together. So you want first of all to express the objective quantity so it could be volume, surface area, cost, product, sum, anything, in terms of the unknowns. So that'll give you a formula. Okay, in the previous example, the objective quantity was x plus y. Right, so it'll give you a formula. Next, identify the constraint. So that means there'll be something in the question which restricts the picture in some way. Okay, in the previous example, the objective was finding the sum, but the constraint was the product had to be 100. So we want to identify the constraint and express it as an equation in our unknowns. Okay, in the previous example, the constraint could be represented by the equation x times y is equal to 100. Next, 5. And this is where kind of the actual kind of procedure comes in. So this is, once you've done this, so 1, 2, 3, and 4 are, I think, conceptually the hardest part of any word problem, because it requires you picking out the relevant information, and that can be difficult depending on the situation. Once you've got this, though, the procedure is almost always the same, and it's more mechanical. So I would solve the constraint, just like we did before. Solve the constraint equation in one unknown. And substitute into the objective. So that's going to make your objective equation no longer a two-variable function, but a single variable function. This will give a single variable. So when I say single variable, it means it's got one input. Single variable function. We'll call it f. That's good, because we can find maxes and mins of single variable functions. We can't find maxes and mins of two variable functions. At this point, if we're going to find maxes and mins relative extrema, we need to know what the domain is, just like I did before. So identify the domain of f, or maybe I should say a bit more careful. Identify the domain imposed by f, the function, and the question, and the problem. So in the previous example, f only said that x was non-zero, but the problem also stipulated that x has to be positive, right? So you may have two things. Okay, so use now the methods, use previous techniques to find absolute extrema. So once I've got the domain, I've got my function, I need to find the absolute max and absolute min. If you're a closed interval, it's quite easy. You just find all the critical numbers and evaluate the function at the points. Absolute max is the biggest, absolute min is the smallest. If you're an open interval, you're going to have to use sign analysis on the derivative and hope maybe the critical number formula appears, or the critical point theorem, should I say, or maybe something else happens. But it's more tricky, okay? So if you're not in a closed interval, it may not work. So finally, I would always say conclude by explicitly stating a solution. To the problem, just like I did a moment ago. And it's very tempting after 6 just to walk away the moment you've got your extrema, but remember you need to relate it back to the actual nature of the problem. Okay, so this, let me zoom this out a bit. This is everything in one place, pretty much. Yeah. Okay, so that's the checklist. So 7 things. It's really important you follow this checklist. Many of you, I know, when you look at word problems, just feel lost. I mean, I feel lost. Word problems are difficult. Like, it's a trick of the trade. The only way to do word problems is to break it down in this manner. Right? There's a temptation to think that people who are good at word problems just look at them and instantly see the problem. That is not correct. What they do is they go through this checklist internally. Okay, so the most important thing is step 1 to 4, in my opinion. Once you've got the objective formula and the constraint equation, the procedure is kind of, as I said before, mechanical. You solve the constraint in an unknown, feed it into the objective, do your usual analysis, get a result. So you can do that without having to think too deeply. But getting the objective and the constraint is the hard part. So my basic advice about getting good at this is to, well, first of all, watch the rest of this video, watch how I do a couple of problems, obviously do the homework, but you should also maybe go through all of the questions at the back of that chapter. So is it 6.2? So even the ones that I've not set for homework, don't necessarily go through the entire problem, that's kind of too much, but do attempt to find the objective and the constraint for each of those problems. If you do that for every one in there, it won't take you that long because you're not having to do all of the kind of the calculus stuff, you're just trying to do steps 1 to 4. If you do that for all of those, you're going to be very powerful, right? You'll be bulletproof. There'll be nothing I can throw at you. And it's a really good way to test yourself on the fundamentals. So let me do an example now. So let's go for the following. So example, let's say a coffee company. So we'll do a practical example now. A coffee company wants to make cylindrical coffee cans with a fixed volume. With volume 1,000 centimeters cubed. It's 1 liter. So here's the question. What should the dimensions be to minimize the surface area? So that's an important question for obvious reasons. If you are making a lot of stuff, you want to do it in the most efficient way possible. All right, there are lots of different shapes which have a volume of 1,000 centimeters cubed. You want to do it in such a way that you're using the least possible materials, which boils down to using the minimum possible surface area. This is a really important question. So let's go through it piece by piece. First of all, before we do anything, what is the objective? The objective is to minimize surface area. So the objective is to minimize surface area. Write that down. So your objective formula is going to involve the surface area. Next, draw a picture. So it's a cylinder. Ooh. Let me try to draw this reasonably. It's okay, just about. So it's a cylinder. So it's going to look something along these lines, vaguely speaking. Okay, so if it's a cylinder, there are 2 dimensions I need to know. I need to know the radius and the height. So the radius, remember, is this length. I'll label this R. And the height is this length. Of course, I'll label this H. These are the dimensions I need to know. Okay, so that's the picture. Fairly straightforward. The next, I need to represent the objective in terms of these unknowns. The objective is the surface area. Now, what is the surface area? It's composed of 3 things. You've got the top, you've got the base, and you've got the sides. So the top is just the area of a circle of radius r, so that's pi r squared. The bottom is exactly the same. What about the sides? Well, this is a bit more difficult. The main thing is, if you have a cylinder, you can, I suppose, kind of cut it down the side and unroll the edges. If you do that, what are you going to get? You're going to get a rectangle whose height is going to be h, but the length is going to be the length all the way around the outside, right, if you lay it flat. So that's the circumference of a circle. So if I think about it, putting it all together, that means the area around the sides is the circumference of a circle, which is 2 pi r multiplied by h. So this is the top, this is the bottom, or the base, and this is the sides. So I can tidy this up a little bit because I've got the same term going twice. 2 pi r squared plus 2 pi r h. So that's it, it's my objective formula. Okay, so this is the objective formula. Next, the constraint. So what is the constraint? So if we look at the problem, the constraint is that the volume is 1,000. So what is the volume of a cylinder? It's the base times the height. So the constraint is that the volume is equal to 1,000. This implies what? Well, the base is pi r squared, the height is h. Product of this has to be equal to 1,000. So this guy is the constraint equation. Okay, so that's in many ways the hardest part done. Right? Being able to accurately pick apart these four things, identifying the objective, drawing a picture, labeling the unknowns, expressing the objective in terms of the unknowns, and expressing the constraint in terms of the unknowns. That's the most important thing about this procedure, as far as I'm concerned. So as I said, if you want practice in doing this, go through the problems in the back of 6.2, even the non-homeworks, and just do this. Don't go through the procedure of actually finding maxes and mins, but find the objective and the constraint, right? It will help you hugely if you do. So at this point, we've got to do the rest. So I need to, first of all, solve the constraint of one unknown. Now there are two choices here. So pi r squared h is equal to 1,000. Well, I can do two things. I could solve for h, which gives me 1,000 is it divided by pi r squared, or I could solve for r. So this would give me 1,000 divided by pi h, but I'd have to take a square root. So either of these approaches will work. I would strongly counsel you to use the first because the formula is easier, right? So you don't have to take a square root in the first case. So often there'll be a bit of asymmetry and you have two possible choices. I'm going to choose this one. That's much the simplest. Okay, so I've got this. So what does this tell me? Well, let's go to the objective. 2 pi r squared plus 2 pi rh. So I'm going to replace h with this. So this gives me 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. Let's tidy this up. This is equal to 2 pi r squared plus 2,000 divided by r. So this now is a combination of the objective and the constraint into a single variable function, which I'm going to call fr. So now at this point, I need to go through the procedure of actually finding whatever it is, the absolute max or the absolute min of this. In this case, it's going to be an absolute min. I'm trying to minimize the surface area. So let's do 6. What's the domain? As before, it comes from two things. One is the function itself. So clearly, looking at the function, it's the same kind of thing as we saw before. R is non-zero, because I can't divide by 0. But are there any other restrictions placed on it? Well, yes. R is a radius. So R certainly has to be bigger than or equal to 0. Any other constraints? Well, if we look at the constraint equation here, notice that I can choose any positive value r. This is the same kind of logic we had before. R could be as big as we want because I can always counterbalance it with a smaller h. So putting this together, I see that the domain is the same as I had before, it's 0 to infinity. Okay. So that's what I'm trying to maximize or minimize on. So I'm going to have to hope for the critical point theorem in this situation. So let's go for it. Okay, so first of all, I need to take the derivative, don't I? So the derivative is equal to 4 pi r, what is it, minus 2,000 divided by r squared. Type A points. F prime of r, F prime of r equals 0. That implies, well, 4 pi r minus 2,000 over r squared is equal to 0. If I rearrange this, this gives me r cubed is equal to 500 divided by pi. So that's me taking the 2,000 over r squared to the other side and cross-multiplying the usual business. So this now implies what? R is equal to the cube root of 500 over pi. So that's a bit of a nasty number, but it's a number, right? It's not so bad. B. So obviously, if I was talking about f on the entire line, or f prime on the entire line, there'd be a problem at 0. But notice I'm only dealing with things which are strictly positive. So f prime is continuous everywhere. On the interval 0 to infinity. Okay, so that means I don't have any type B points. So at this point, it's time to do my sign analysis and hope that something reasonable happens. So what have I got? I've got my point cube root of 500 divided by pi. Okay, so now at this point, what do? Well, we don't necessarily have a calculator to work this out, but we can use a bit of quantitative reasoning. I mean, 500 divided by pi, 500 divided by 3-ish, and then we're taking a cube root. I mean, that's definitely less than 100, I would say with some confidence. So on this side, let's think about f prime of 100. Now, f prime of 100 is what? If I feed it in, it's 400 pi minus 2000 divided by 100 squared, so that's that. That's definitely positive. So I'm definitely positive on this side. 500 over pi is bigger than 1, so the cube is bigger than 1. So on this other side, we could check f prime of 1. Well, that's equal to 4 pi minus 2000. That's definitely negative. Notice here as well, it's a critical number at this point. It's defined, or the function is defined. So I'm going down here, and I'm going up here. So I can employ the critical point theorem now. So this implies f of root 3 500 over pi is an absolute min of f on the interval 0 to infinity. So now I've got to draw all this together into one conclusion. So maybe just before I do that, so this absolute minimum is occurring when r is equal to the cube root of 500 over pi. And remember, h is equal to, what was it equal to? It's 1000 divided by pi r squared. So in this instance, this tells you h is equal to, it's not the nicest number ever, it's 1000 divided by pi times the cube root squared, so it'd be 500 divided by pi to the power 2 over 3. So the conclusion is, and this is step, what is it, step 7. Surface area is minimized. It is minimized when the radius is equal to this lovely expression, the cube root of 500 divided by pi, and h is equal to 1000 divided by pi times 500 divided by pi to the 2 over 3. There we go. And if you wanted the actual surface area, you would need to evaluate f at the cube root of 500 over pi. So that part of the procedure is a bit tricky, obviously, because without a calculator we don't know exactly what the cube root of 500 over pi is. I mean, in a real world situation you would have a calculator, but I think this is a reasonable level of difficulty for a midterm, because we can use some quantitative reasoning to decide that 100 is bigger than it and 1 is less than it, for example. Okay, but again, the most important part of this procedure really is identifying the objective and the constraint. So let's do another one. So example. So this one is going to be more difficult in terms of identifying the objective and the constraint, but maybe easier in terms of the actual mathematics afterwards. So a supplier wants to create an open box from a 12-inch by 12-inch square of metal by cutting the squares, or by cutting squares from the corners and folding up the sides. what is the maximum possible volume? This is a great question because it highlights a few issues with this whole procedure. First of all, what are we trying to do? What's the objective? The objective is to maximize a volume. That's it, right? The next, I need to draw a picture. This is quite a complicated situation. So what's actually happening here? Well, let me draw what's going on. So it's up to you to kind of pick this apart. So let's draw my sheet of metal, 12 by 12 apparently. Now what's going on is I'm cutting squares of unknown dimension out of the corners, aren't I? So they're all meant to be the same, and I'm removing them. So once I've removed them, what am I going to do? I'm basically folding up each of the sides at these lines. Okay, so once I've folded this, what do I get? I'm going to get an open box like this. Damn it all. So I'm going to get some open box. Good enough. Okay, so I need to quantify this in some way. It's a box, right? So definitely, if I'm talking about volume, I should just label its dimensions. Now take a look. I'm starting with a square. This means the base is going to be square, which means if I label it, let's label the base y. Let's do this for fun, I don't know. I could use x, I'll just use y for the hell of it. So these are both the same dimension. Right? They're the same dimension because it's a square base. There's another thing I need to label, it's the x. It's the height. So if I go back to this picture over here, I can mark this information in. I mean, this length here, that's your y. Yeah? And if you want this length here, which is the same for each of them, this is your x. So this is me quantifying the picture. I've drawn a picture which really illustrates what's going on. It's good to do both of these, both the box and kind of the flat sheet. And I think from this I know everything. So the next is I need to tell you, we need to work out what the objective is in terms of this unknown. So what is the objective? Well, the objective is equal to the volume, right? So the volume is equal to what? Base times height times width. It's going to be y squared times x. Okay. So this now is equal to your objective formula. Next, we need to identify the constraint. Now, this is a bit trickier. What is the constraint? The constraint is, well, the only constraint really is the sheet of metal is 12 inches by 12 inches. So the square sheet is 12 by 12. In particular, it's 12 inches long. So what does this mean? Well, what's the length in terms of x and y? Notice all of these are the same. So it strikes me that x plus y plus x has to be equal to 12. That is the constraint, as outlined by this question. So this is one of the harder parts of it, I think. So this implies what? Well, I can tidy this up a bit. 2x plus y is equal to 12. Very nice. Okay, so at this point, we're kind of cooking. We've got my constraint formula, or constraint equation, sorry. We've also got the objective formula. So I just need to solve the constraint in one unknown, feed it into the objective. So there are two ways to do this. I'll do one which maybe isn't the most sensible in some ways, but kind of fits with the usual pattern of doing things. Let's solve for y. So 2x plus y is equal to 12. This implies y is equal to 12 minus 2x. Okay, great. So now what's the objective? The objective is that, the volume. This is equal to, well, I just replace this, 12 minus 2x squared times x. Okay, so this now, it's a bit of a nasty thing. If I'd solved for x actually and fed in, it would be a simpler formula. But there's no harm in doing this, and I'll multiply this out. I think if I multiply this out, I get 144x minus 48x squared plus 4x to the 3. Okay, so this now is what I'm going to call f of x. So that's the thing that I need to maximize or minimize. Some of you may be looking at this and saying, do I really need to go through this procedure with two variables? I think when you do this problem, some of you may well, when you've drawn the original picture, so this is kind of as an aside, when you did the original picture, you might have immediately observed that, well, this length is 12 minus 2x. So I don't really need to have two variables to do this picture. I could have removed this and I could label this 12 minus 2x here and 12 minus 2x here. Then, basically, if you notice, when you write down the volume, the objective, you'd immediately skip to this stage. That's a perfectly valid way to do this. One thing about it that's a bit more difficult is you're kind of, once you draw the picture, you are baking the constraint directly into it. So in other words, you're doing kind of steps 2, 3, 4, and 5 simultaneously if you're trying to do it with one single variable. So that's the reason that I decided to put a y here and avoid doing this in one go, just because it compartmentalizes my thinking, so I'm less likely to make a mistake. Okay, the bottom line is I need to maximize or minimize this guy. Is it minimize? No, it's maximize. Okay, so 6, domain. Now this is super important in this problem. So we're trying to find an absolute max for the function. So let's take a look at the function. The function is this guy. And if you notice, that's a cubic equation. That means it's going to get bigger and bigger and bigger as x approaches infinity. So we know overall f does not have an absolute maximum. Not if I'm taking the domain to be the entire number line. Certainly not if I'm taking it infinitely in the positive direction. So if you try to do this process of finding an absolute max of this without working out the domain ahead of time, you're going to run into a major problem. And let's take a look at the domain in this case. So first of all, f, well, the domain of a polynomial is everything. We need to think carefully about what restrictions are placed on x by the problem. So let's go to the top. First of all, clearly, x is bigger than or equal to 0. Okay, you can't have negatives here. Also notice, well, actually, let's take a look at the constraint equation. So the constraint equation tells you what? Well, you've got, so 2x plus y is equal to 12. Now y itself has to be positive 2, right? So that means that 12 minus 2x has to be positive. That means the biggest possible value x can be is 6. If x gets bigger than 6, I mean these squares would overlap in the corners, which doesn't make any sense, and y would become negative, which doesn't make any sense. So the biggest possible value, so if I go up here, maybe mark this on, remember this is 12. The biggest possible value x can be is 6, because it's half 12. So the problem imposes this condition. So this means the domain I'm interested in is 0 to 6. 0 to 6. Okay, so really important here, we do this carefully. So if you didn't do this, you wouldn't be able to find an absolute maximum. So then, it's a closed interval. Brilliant. It basically means I don't have to do my sign analysis, particularly to evaluate at certain points. So what have we got? Let's go for it. Let's take the derivative. So f prime of x is equal to 144 minus, what is it, 96 x plus 12x squared And if I factor this, it turns out, well, you can take a 12 out. If you spend a bit of time messing around with it, you get x minus 6, x minus 2. Okay. So x minus 6, x minus 2. So now what do I need to do? Well, I need to check my critical points if you want. So A, f prime of x is equal to 0. This implies that, well, either x is equal to 6 or 2, so it's 2 or 6. B, I mean, it's a polynomial. F prime is continuous everywhere. So no need to worry about this. So this tells you that, well, the endpoints and the points interior are, so 0, 2, and 6 are all critical numbers on the interval 0 to 6. So now I just need to evaluate all of them. So f of 0 is equal to 0. Turns out that f of 2 is equal to 128, sorry. And it actually turns out, I hope this is correct, that f of 6 itself is equal to 0. So what does this tell you? This tells you that f of 2, which is 128, this is an absolute max. On the interval 0 to 6. So the conclusion is 7. The box has maximum volume of 128, I suppose, is it inches squared, or inches cubed, sorry. This occurs when the height is 2. So maybe up here it's actually worth saying, if x is equal to 2, what's y equal to? So y, remember, is equal to 12 minus 2x. Okay, so this two things imply what? 12 minus 4 is equal to 8, so y is equal to 8. And the height is 2 inches, and the base 8 by 8 inches. There we go. So that's basically how you solve these problems. So mathematically, the bit at the end, in terms of doing the max and min, was quite easy in that problem. The hardest part by a mile was identifying the objective and the constraint effectively. And there are different ways to do this, as I say. This is one of them. The main thing is go through the checklist. It is absolutely crucial that you go, first of all, to find the objective, draw a picture, express the objective in terms of your unknown quantities, think what is the constraint in the problem, express it in terms of your unknown quantities. Right, so those 4 steps are the most important part of solving any word problem. And as I said before, look at the questions in 6.2, even the ones that aren't not in the homework, and go through them and just do check like 1 to 4. Just find the objective and the constraint for each of them. That without doing the kind of the calculus part at the end, as I said. So just do that, it'll make you much better at this, much more confident. So there we go.